Hi, it's Ms. Hochstetter to show how to solve problems using physics. So there's kind of a method that works best for learning how to solve physics problems, and this is also a really good strategy that you might want to use on like the math SAT, for instance. It's just a really good strategy to help you organize the problem when you get to it. So the first step is to read and annotate. So you're going to want to make sure you read the problem and understand and know what it's asking you to do. And when I say annotate, I mean a few things specifically. So you're going to underline key information. So key information can be numbers and units in the problem itself. It can also be key phrases. So key phrases might be word clues that tell you a little thing about what's happening in the problem. Like, for instance, with motion, if it says starts from rest, that's not a number that you would underline, but it is starts from rest implies that it starts at 0. So that would be a good key phrase to underline. Or even, like constant velocity is another good phrase to underline. Key information, again, just any number. And there might be numbers that are given to you that you end up not needing, but it's just helpful to underline all of those. And then you're going to circle what it's asking for. So that's what I mean by annotating the problem. Then after you read and annotate, you're going to label your variables. So you're going to look at the words that you underlined and the numbers that you underlined, and you're going to see if you can figure out what variables they belong to. This is going to set you up to be able to pick out an equation from the reference table. So I'm going to go ahead and use this example here. This is a very, very straightforward example. Like, you probably don't even need to use this method to solve it. However, as we advance, we're going to get to problems that have 4 or 5 variables in them, and it's going to get confusing. So I'm just starting with the most basic example to help us with this. So it says a car travels at constant speed of 12 meters per second for 72 meters. How long was it moving? So I'm definitely underlining the numbers and the units. How long, that's what we're looking for. We're looking for a distance. And then also this constant speed may or may not become important to us as we try and solve for this. So that's how I would annotate. So now that I've annotated it, we want to label our variables. So this 12 meters per second, that's going to be a velocity. And we know that because the units are meters per second. And it also says it was traveling at a constant speed. 72 meters, that's going to be a distance. And how long it was moving. Oh, I'm sorry, I said that was a distance earlier. How long was it moving? That's going to be a time. So what we're going to do, so we labeled our variables. I usually like to make a little key. So 12 meters per second equals V, D equals 72 meters, and then T equals question mark, because that's what we're trying to solve. So we've done steps 1 and 2. Then we're going to pick an equation to use. And this is often where I find students struggle the most with physics. So I'm going to scroll down to the reference table that I have here. I just copied it. We want something that has V, D, and T for an equation. And again, I said this problem is relatively straightforward. It's not super complicated. But if we look at this first one here, we see we have V, D, and T, where velocity, with the line over it, that's your average velocity. D is your distance and displacement, and T is your time. So this is the equation we're going to use. But you can see, like, especially when we get down here, these equations get more complicated. So even though we're just doing this one up here, later down the road, we're going to be using these other equations, and that's where it can get confusing if you don't know this method. So what I'm going to do is I'm going to write that equation, V equals D over T. So we picked our equation to use. Now we're going to substitute our variables in. So like V is going to go in for V. My distance is going to go in for distance, and then I'm going to solve for T. So I'm going to substitute that in. 12 meters per second equals 72 meters divided by T. So I substituted my variables in to the equation with the units, and now I want to solve for T. So to solve for T, I need to get it out of the denominator, so I'm going to multiply by T on both sides, so that goes away, and I get 12 meters per second times t equals 72 meters. Then I'm going to divide by 12 meters per second. That goes away, divide by 12 meters per second. And what I'm going to be left with is 72 divided by 12 is 6, and then seconds. Now, I do want to go back and talk about the units, how we get that, but that would be how we solve for the unknown variable. That's how we would solve the problem. But let's talk again about these units here, because it's meters divided by meters per second. That's like the same thing as saying meters divided by meters per second. To divide by a fraction, what do? We keep the first one, we change this to multiply, seconds over meters, and you see that the meters cancel out and we are just left with seconds, which is exactly what we should get because we're solving for a time. So that would be how we do this. I know this particular example is not super difficult. As we move forward with our physics curriculum, these problems are going to get more complicated, but I wanted to introduce the problem solving for physics for this. All right.